Oh, I forgot to, hold on a second. I got to delete this one. That was the intro. Don't save. Let's get to here. All right, here we go. Because that's being loaded on YouTube. Right? You want to see what I do? In other words, so now we go to Google, and here's what I do. I click here, and then it says upload a file. So like, if I click here, oh, stay. Yeah, it's in the middle of processing that little 2.5 minute thing, and this thing is very misleading. It's probably almost done, and I've found that loading files to YouTube is a lot like quantum mechanics. If you don't watch it, stuff happens. When you watch it, nothing happens. Okay, so let's stop watching it. I'm sure you're all just thrilled by that. Anyway, so with some trepidation, I'm going to do this. I'm going to do this this way. The only thing I worry about is my big hairy hand showing up, which is kind of not very aesthetically pleasing, I guess. All right, so here we go. A man drops a rock into a dark well. All right, using precision equipment, you measure the time that elapses until the sound of the splash reaches your ear. Splat. Okay, so you drop it, splash, and due to the height of the well or whatever, we're going to say ballpark. We can pretty much figure the height. Calculated Calculating numerical value is expected and not an expression. Okay, so here we go. So neglecting the time for required sound to travel back up the well to that fancy equipment that we have. Calculate the depth to the surface of the water. In other words, you drop it and it goes plunk, okay, in meters if the sound returns in 1.5 seconds. Okay, so we're not going to calculate for that extra little bit of the sound coming back to us. And so it becomes an easy problem. We're just going to drop a rock. Splash. Okay, so it splashes here. And the time it took was equal to 1.5 seconds for our purposes. Well, we know the acceleration is equal to negative 9.8 meters per second squared. Now, if they give me an answer in positive values, I'm going to be a little upset. Okay, I'm going to be a little bit, the distance of travel should be a negative number. But anyway, so here's what we're going to, so that's fine. Anyway, I haven't worked, I probably should have worked this out before I brought you all into the mix here. All right, but anyway, we know that the distance then is equal to, because the initial velocity is equal to 0 and the y direction is equal to 0. So I know that it went d is equal to gosh dang it. Because I want to do this right. Okay, I don't want to just, so in other words, I drop it from up here. I've got an h naught, which I don't know, but I know h final is equal to 0. So I'll go 0 is equal to h naught plus v naught in the y direction times t, which we know that's going to 0, minus 1/2 gt squared. And they gave me the time, which is sweet. So if I add this 1/2 gt squared to both sides, I'll get a positive 4.9 times t squared. Okay, so if I'm taking the initial height of the well, then it will be a positive number. So that's good. Times t squared is equal to h naught, and t squared was equal to 1.5 seconds. So as usual, I'm all ready to go, but I don't have my calculator with me. There's all the calculations we did today in class. All right, so I've got 4.9 times 1. For my problem, it's 1.5 squared in parentheses, boom. And it's 11 meters, 11.02 meters. I'm going to go with 11.02 meters as the initial height. That's great. I'll put that in. Okay, so I got 11.02 meters, and I'll buy that. That's the initial height. Okay. Now, if your answer, if it says it's wrong, check the sign. Try a negative, and we'll see what happens. I haven't worked this out. Now, this is where this thing gets crazy. All right, this is where this is a little bit crazy. So I'll do part D. I'm going to stop here, and then we'll do part B.